Yes, hello students. In my previous lecture, I explained what is the uh, thermal loading of motor. When the motor is loaded, the heat is generated inside the motor because of copper losses and iron losses, and the temperature of the motor increases. As the temperature increases, the heat dissipation increases, and when steady state comes, the heat generated becomes equal to heat dissipated, and the motor reaches the steady state temperature rise. Similarly, when the motor is unloaded or disconnected, the power loss becomes zero or very low, and the motor cools down to the new value of temperature rise. So, now in this lecture, we shall discuss what are the different types of loading and how to select the rating of motor for different types of loading. So, this is I will discuss in today's lecture. So, how to determine the motor rating for various applications. So, let us first discuss the three main types of loadings that the motor may be subjected to. So, the first case is of continuous duty, the second is short time duty, and third is intermittent periodic duty. So, what is the meaning of continuous duty? As the name suggests, the motor is loaded continuously. That is, it is loaded for enough time that the motor reaches the final steady state temperature rise depending on the load on the motor. So the time for which the motor is loaded is more than or much more than the thermal time constant or heating time constant of the motor. So motor will heat up as the motor is loaded, and finally it will reach the final steady state temperature rise. So this is known as continuous duty. Short time duty, here the motor is loaded for the time say TR running period, and then it is unloaded or disconnected. So this time TR for which the motor is loaded, this is much less than the heating time constant of the motor. This means that during this time period, the motor will not reach its final steady state temperature rise, and after that the machine is disconnected, and it is disconnected for long enough time so that the motor again reaches its ambient temperature. So this type of duty is known as short time duty. Third type of loading that you may get for the motor is intermittent periodic duty, where the motor is loaded for time TR, where TR is the running period or loading period, and this is much less than the heating time constant of the motor, and then it is disconnected and stopped, or you can say stopping period for time TS, where TS is much less than the cooling time constant of the motor. So this means that during the loading period, the temperature does not reach the final steady state temperature rise, and during the off period, the temperature doesn't reach the ambient value, ambient temperature. So this type of duty is known as intermittent periodic duty. You have to move something, or you have to cut something, and then again you have to come back and again cut it. So like that you will have this type of loading. Some pressing machine may be there. So there this type of loading may be there. Now how to select the rating of the motor for the particular application. So this is our discussion today. So let us first take the most easy and common type of loading, that is continuous duty, where the motor is loaded continuously for say 5 hours, 6 hours, 3 hours, 2 hours, like that. In that case, what you have to do, simply you must know what is the power rating, demanded by the load. So that power is ascertained, that what is the continuous power demand of the load. For suppose it is 38 kilowatt. So you can select a motor of rating 38 kilowatt or more than that, depending on the availability in the market. So you have to select the rating which is equal to or higher than the commercially available ratings of the motor. So in that case, for example, 38 kilowatt is the maximum demand, the available rating is 40, you'll have to select 40 kilowatt motor. If available rating in the market is 45 kilowatt, you have to select the motor of 45 kilowatt. So in that way you can select the rating of the motor. So that is very simple. Now suppose you select a motor of small power rating. For example, the demand was 38 kilowatt. Available motors in the market was of 30 kilowatt, 35 kilowatt, then it is 45 kilowatts. So instead of using motor of 45 kilowatt or 40 kilowatts, you decided to select the motor of say 30 kilowatt or 35 kilowatt, lesser than what is the maximum demand of the load. In that case, you will have certain advantages and certain disadvantages. So what will be advantage? Advantage will be that it will be less costly. You have saved some money. So that is the advantage of selecting the motor of lesser power rating than the required by the load. But it will have certain disadvantages. It will not be able to produce the output that is desired by the motor. For example, you are running some pump, and if you are selecting the motor of lesser power rating, the water flow from the pump will be reduced. It will not be as you expect from that pump. So that is fall in production level. Number 2 is less reliability. That is, when you load it continuously, then what will happen? That the temperature rise of the machine will be more than the temperature rise for which the machine is designed. It will be overheated. So what it will do? It will reduce the life of the motor, and you will have frequent failures. You have to go for maintenance several times. So this will reduce the reliability of the motor, and moreover you can say that the lifespan will also be reduced. So you can say that it will burn out earlier. So lifespan will also reduce. So the motor which you expected to last for 10 years may last in say 5 years. Because of continuous overheating, the insulations and the windings will burn out earlier. It will damage, and the motor will have to be discarded earlier than the expected life of the motor. So this is the case when you select the motor of a smaller power rating. And suppose you have selected a motor of larger power rating, then advantages are, it will give you a very high production level. You will get a good result from the motor, and it will be highly reliable, because motor is never loaded to its rated capacity. The temperature rise of the motor will be less than the permissible temperature. So the motor's life will increase and its reliability will be high. So you can say the high reliability. And the third advantage you can write here, that high lifespan. That is the motor which was supposed to last for 10 years. It may run up to 15 years or 16 years like that. Disadvantages that you will face here, it will be having a high initial cost. Of course, you are selecting the motor of higher power rating, the cost will be higher. That you have the option of selecting a motor of 40 kilowatt or 45 kilowatt. You have chosen the motor of 45 kilowatt. So this means in that case the cost of the motor will be high. And also it will be less efficient. Higher the motor power rating, more will be the iron loss, continuous loss, and it will have less efficient motor. You know that of any machine, the efficiency curve is like this: efficiency versus load. So if the motor is underloaded, you are here somewhere, efficiency is less than the case when you properly loaded the motor and you got the maximum efficiency of the motor. So efficiency will be less, higher iron losses will be there, that will reduce the efficiency of the motor. And the third thing that may be there, that it will have a poor power factor. In case of induction motor, you know that induction motor has two components of current. Suppose you apply the voltage here, the shunt branch current and the other is the load current. The current drawn for magnetizing purpose, that is Im, will be high if you have the motor of higher power rating. So this will have the poor power factor as well. So these are the three disadvantages that you will face when you select the motor of larger power rating. So therefore, you have to take a judicious decision. Neither you select the motor of much lesser power rating, nor you should go for much higher power rating. Both have their advantages and disadvantages. So you have to take a judicious decision how to select the rating of the motor for continuous duty load. Now we shall discuss how to select the motor rating for short time duty and intermittent periodic duty just now. So we shall now discuss how to load the motor when the load is of short time duty type. So here this figure shows that the running period is TR and the rated power of the motor is PR. So if we connect a load of PR across the motor, that is the rated load of the motor, in that case the motor's temperature will rise and it reaches somewhat at this temperature theta R at the end of loading period. After that, the cooling of the motor will start taking place. But this temperature theta R, for which the motor, the temperature rise of the motor during this loading period is much less than the permissible temperature rise of the motor. So when it is a rated load and the motor is connected with the rated load for long enough time, in that case the motor's temperature would rise to the value of permissible temperature rise of the motor. But we are disconnecting the motor here and after that the motor cools down, and you can say that the motor's temperature rise will be much less than the permissible temperature rise of the motor. Or you can say that the thermal capacity of the motor is not fully utilized. So during this loading period, that is time interval TR, the temperature of the motor will rise as per the equation that we discussed earlier also. Theta is equal to the steady state temperature rise, that we have called it theta permissible 1 minus e to the power minus t upon tau h, the heating time constant of the motor. So if the motor is loaded only for this much time, at the end of duty period, that is T equal to TR, the temperature will reach a value that you can write here. Theta R is equal to theta permissible 1 minus e to the power minus TR upon tau h. So during this loading period, the temperature reaches the value of theta R. So this equation let me call as equation number 1. And of course, if TR is much less than the heating time constant of the motor, then theta R will be much less than the permissible temperature rise of the motor. And in case if TR is much greater than tau h heating time constant, then the temperature rise will be equal to theta permissible. So what you can say that in this case TR is much less than tau h, so the temperature rise during this period is much less than the permissible temperature rise. So what we can do is now we can overload the motor, or you can say for a given load demand you can select a motor of lower power rating. So in this case, let us say we are the rated load of the motor, then you can put a higher load on the motor by a factor K. So if we are loading the motor by a factor kPr, so if the motor load or motor is loaded with power P dash, which is equal to K times the rated power rating of the motor, then the temperature rise of the motor can be written as theta is equal to theta SS 1 minus e to the power minus t upon tau h. Now here theta SS is the steady state temperature rise if the motor is loaded for a load of P dash, that is equal to K times PR. That is, if you connect this load continuously, in steady state the temperature will rise to a value theta SS that will be much more than the permissible temperature rise of the motor. So this is theta equal to theta SS 1 minus e to the power minus t upon tau h. So what will happen? We have to overload it such that at the end of duty period or the running period, the temperature reaches the permissible temperature rise. That is, at T equal to TR, the temperature of the motor should become equal to the permissible or the rated temperature rise of the motor, that we are calling theta PER, and that is equal to theta SS 1 minus e to the power minus TR upon tau h. TR upon tau h. So we have overloaded the motor such that steady state temperature rise is theta SS, and in that case at the end of duty period the temperature becomes equal to theta permissible. That is, you are fully utilizing the thermal capacity of the motor. After that, after reaching this point, you can disconnect the motor and the motor will cool down to ambient temperature before it is loaded again. So motor will be safe, it is not overheated, but you have utilized the full thermal capacity of the motor. Say the value of K for particular case comes out to be 2. This means that a 100 kilowatt motor is loaded for 200 kilowatt and still the motor is safe. Motor will not be overheated, its temperature rise is within the safe limits, that is the permissible temperature rise of the motor. So if you are able to do that, we are fully utilizing the thermal capacity of the motor. Now let us write equation 2 in a different way. Equation 2 can be written as theta SS upon theta permissible is equal to 1 upon 1 minus e to the power minus TR upon tau h, heating time constant. Let me call this equation as equation number 3. Now again, you just remember that theta SS is the steady state temperature rise when the motor is overloaded by a factor K, and theta permissible is the steady state temperature rise when the motor is loaded for its rated power rating. So now this theta SS will depend on the power losses in the overloaded condition, whereas theta PR depends on or is proportional to the power losses under the rated loading condition. So this you can write that this is P losses at the overload condition, and this is P losses under the rated condition. So this is equal to 1 minus TR upon tau H. So theta SS is proportional to PL dash, whereas the theta PR is proportional to PL, that you may call as PLR, that is the rated power loss, and this PL dash is the power loss in the overloaded condition when the load is equal to P dash, which is K times the rated power. Now this PLR, that is the power losses in the rated load condition, will comprise of two constants. Let me call this equation number 4. So this will be having two components, the constant loss component and the variable loss component. So you can write it as PC plus PV. Constant losses, that is iron losses, and variable losses. So let me call this equation as equation number 5. And what will happen when the motor is loaded, overloaded? Constant losses, that is iron losses, will remain same, but the variable losses will change. And variable loss depends on square of the current. Current is proportional to power. So this means that if the motor is overloaded by a factor K, the variable losses will increase by a factor K square. So what will be the value of P L dash? It will be equal to constant loss plus K square variable loss under rated power condition. So this equation, let me call it equation number 6. Now let us assume that the copper loss or the constant loss is some fixed percentage of variable loss. So let us assume that the constant loss is alpha times the variable loss. So in that case, equation 5 will become PLR is equal to alpha PV plus PV, that is 1 plus alpha times P. And equation 6 will become PL dash is equal to PC, we are taking as alpha times rated variable loss plus K square PV. So you can write it as alpha plus K square PV. So let me call this equation as equation number 7 and this equation is equation number 8. Now you can put the values of PLR and PL dash from equation 7 and 8 in your equation number 4. So this will imply that PL dash is alpha plus K square PV and PLR is 1 plus alpha PV, and this is equal to 1 upon 1 minus e to the power minus TR upon tau H, heating time constant. So this PV cancels out and you can solve this equation as, so it's alpha plus K square, so you can take it on this side. So you will get alpha plus K square is equal to, on this side is 1 plus alpha upon 1 minus e to the power minus TR upon tau H. You can take alpha on the right hand side, minus alpha, and then you can take a square root of this. So this is the expression for K. We call it equation number 9. So this means that the motor can be overloaded by a factor k, which is given by 1 plus alpha 1 minus e to the power minus tr upon tau h minus alpha. So this means that the lesser the value of tr, higher the value of k. So lesser the time for which the motor is loaded and higher you can overload the motor. So if the loading period is very small, the factor of k may come as 3, 4, 5, 6 depending on how small is the loading period. But you cannot overload the motor indefinitely. That is, there is some upper limit of the overloading of the motor, because in the case of DC motor, there is some upper limit for the current that we can draw from the motor. Not from the heating point of view, but because of commutation point of view. If the current is more than double or 2.5 times the rated current, then it will cause problem in commutation and you will have sparking at the brushes. Current will not be properly commutated and the sparking will occur at the brushes, and that will reduce the life of the brushes as well as the commutator. So you cannot overload the motor by a factor more than say 2.5 times for a normal DC motor. For specially designed motors, we can have the current more than that limit, maybe say 4 times or 5 times. So whatever the permissible current, you have to see. So if the permissible current is twice the rated current, then the value of k cannot be more than 2. If it comes out to be 2.5 or 3 or 4 because of very low value of TR, then you have to limit yourself to load the motor up to the required or the permissible current of the motor. Similarly, in the case of induction motor, if you overload the motor, the torque will also increase and the motor has a particular breakdown torque. You cannot go beyond the breakdown torque of the motor. So that limit has to be seen before you overload the motor. So if the breakdown torque is twice the full load torque, you can go up to twice the rated load on the motor. Otherwise the motor will cross the breakdown torque and it will come to a standstill. So this you have to take care. Sometimes we don't know the relation between PC and PV, that is alpha is not known. We don't know that what is the constant loss in relation to the variable loss. That is, their values are not known separately. In that case, you can assume that the losses are proportional to square of the current, and in that case you can find out if you just follow the procedure again, or you can simply put alpha equal to 0 here, and then the overloading factor will be equal to 1 upon 1 minus e to the power minus tr upon tau h. So if the losses are not known separately, then you can assume that the losses are proportional to the variable loss, and in that case you will get the expression equal to k equal to 1 upon 1 minus e to the power minus tr upon tau h. So in that way you can select the motor of a lesser power rating and you can overload the motor as per the required load of the motor. So this means that this was the rated demand of the load, and you have chosen a motor of lesser power rating. So in that way you are reducing the initial cost of the motor without overheating the motor, without sacrificing the life of the motor. Motor will run its normal life. If it is to last for 10 years, it will last for 10 years. It will not, the life will not reduce. So you can safely overload the motor provided you know what is the loading pattern. If the motor is designed to give a service in which the loading period is very small and that is followed by a long shutdown period, in that case you can overload the motor accordingly and you can optimize the cost of the motor. So in the next lecture we shall see how to select the overloading factor in the case of intermittent periodic duty. Thank you for today.